Can you see the screen?
Yes.
Okay. So now we are going to discuss about heat transfer through a plane wall. Okay.
Yes.
Now, see here. In this is a plane wall. Try to understand. Here we are considering one-dimensional.
Axis.
Okay.
Yes.
X-axis. One-dimensional means we will take one direction only. The other direction we will consider it as temperature.
Temperature. Yes.
Okay.
Yes.
Now, the thickness of this wall is considered to be dx or L.
Yes.
Okay, dx or L. Now, this side of the wall is at temperature T1, the other side is at temperature T2. And if T1 is greater than T2, then heat transfer takes place in this particular direction.
Yes, sir.
Now, as we have seen general heat conduction equation in the Cartesian coordinates. So what does it say? D square T by dx square plus D square T by dy square plus D square T by dz square plus Qg by K is equal to 1 by alpha into dt by d tau. This is the equation we have got. See, whenever we consider a plane wall, here there are certain assumptions that we need to consider. The first assumption is one-dimensional, steady state, without internal heat generation. There is no internal heat generation.
Yes.
Okay. So, in this case, one-dimensional means y and z axis we don't consider. So, d square t by dx square. Okay. So, then here no internal heat generation, Qg becomes 0.
Yes.
Steady state means dt by d tau becomes 0. That means RHS term also becomes 0. So, finally the equation gets reduced to d square t by dx square is equal to 0. Okay. So, now what is our requirement here is that we need to determine how heat transfer is taking place through this plane wall. The second thing is how will be the temperature distribution within this thickness of the wall. Okay, whether it is linear, parabolic, hyperbolic, logarithmic, we need to determine that.
Yes, sir.
So for that, what we need to do is we need to determine the temperature. That means what we need to do here, we need to integrate this equation twice so that we will get T. Correct or not?
Yes, sir.
So in order to do so, what is required here? We need to take on integration dt by dx is equal to constant of integration. So this is on the first time integration basis.
Yes, sir.
Okay. So on integration 0 becomes a constant. So we write like this. Again integrating this, we get T is equal to C1x plus C2, right?
Yes, sir.
So this is equation 2. Now if you observe carefully, is this second expression in the form of y equal to mx plus c?
Yes, sir.
So y equal to mx plus c is the equation of a straight line.
Yes, sir.
So that means, can we consider that within this thickness of the wall, the temperature distribution is linear?
Yes, sir.
Within this thickness of the wall, can we consider the temperature distribution to be linear? So as T1 is greater than T2, along the thickness, this temperature drops.
Yes, sir.
Okay. Then we got this one. Now what we need to do? There are certain boundary conditions which we come across. Okay. So this thickness we have considered it to be dx, or we can write it as L. Correct?
Yes, sir.
Now the boundary conditions are at x is equal to 0. Temperature T will be equal to T1. That means this part of the wall, this side, the left side of the wall. Can you observe?
Yeah, sir.
Then at x is equal to 0, if I substitute in this equation, what will happen? T1 is equal to C1 into 0 plus C2 we are going to get. So that implies C2 is equal to T1.
Yes, sir.
So C2 value we have got. Okay.
Yes, sir.
Now what we need to do after getting C2? We want C1. So let us consider the other boundary condition. What is the other boundary condition on the right hand side? That means at x is equal to L. At x is equal to L, what is the temperature? T2, correct?
Yes, sir.
So then what will happen? T2 is equal to C1 into L. Instead of C2, what we have got?
T1.
T1. So from this, can we write C1 is equal to T2 minus T1 by L?
Yes, sir.
This is one more equation which we need to consider.
Yes, sir.
C2, C1 both you have got. Okay.
Yes, sir.
Now what we need to do after getting C1, C2, we need to determine the temperature at some distance x. Okay. So in order to determine the temperature at some distance x, we have got an equation, that is equation 2. Can you observe this? T is equal to C1x plus C2. So temperature at some distance x can be written in the form like this. T is equal to C1. What is C1? What is C1 that we have got here?
T1. No,
Huh?
sir. T1 minus T2 by L.
T2 minus T1 by L into x plus C2 is T1. So from this, can we write like this? T minus T1, correct,
Yes, sir.
is equal to T2 minus T1
T1 by.
L into x.
Yes, sir.
Can I write like this? T minus T1 by T2 minus T1 is equal to x by L.
Yes, sir.
This is what we have got here.
Yes,
Now, what I am going to do here is, if I want to determine the temperature T at some distance x, if I know the outer layer temperatures, that means this side of the wall temperature, the other side of the wall temperature and thickness, it's very easy to determine.
Yes, sir.
Okay. Now, the next thing is, here our goal is to determine the heat transfer also. Correct or not?
Yes, sir. Yeah,
So we have got temperature distribution to be linear, and by using this equation we can determine temperature at some distance x. Now we want heat transfer. What is the formula for heat transfer? Minus Ka into dt by dx. Correct?
Yes, sir.
So dt by dx here, what we have got in the equation 1, is it equal to C1?
Yes, sir.
So dt by dx is equal to C1. So therefore, what we can write in this particular case, minus Ka into C1 minus Ka into C1 is T2 minus T1 by L. So can we write from this T1 minus T2 by L by Ka?
Yes, sir.
So this is the formula for heat transfer. See,
Yes, sir.
we have learned this same expression in Fourier's law of heat conduction, if you remember.
Yeah, sir.
So the assumptions of Fourier's law of heat conduction are these only: one dimensional steady state without internal heat generation, And
Yes.
this denominator term, we named it as the thermal resistance due to conduction.
Okay.
So this is the formula for heat transferred through a plane wall. Is it clear?
Yes, sir. Is this a derivation, sir?
Yes.
Okay, sir.
Okay. So now let us see the composite wall condition. So composite wall means here when two different materials are joined together, then we will come across this composite walls. Okay.
Yes, sir.
So where do we see these composite walls usually?
Uh, when two walls are attached or normally in malls.
Yeah, normally in malls, in some air conditioned auditoriums. Okay. So you will see these composite slabs, right?
Yes, sir.
Now, see, these composite walls means, for example, if you see, when two different materials are joined together, they will have two different thermal conductivities. Let us say thermal conductivity of the first slab as K1. Okay.
Yes, sir.
So thermal conductivity of the first slab is K1
K1.
and that of the second one is K2.
Yes, sir.
Okay.
Yes, sir.
Now, the thickness of these two slabs are L1 and L2. This is L suffix 1, L suffix 2 here. Okay.
Yes, sir.
Now, heat transfer is taking place in this particular wall. Now, try to understand one important thing here is, now, when you consider this composite slab, you will come across three different temperatures. Can you see here? T1, T2, T3. So T1 is the temperature of this side of the wall. Okay, composite wall. T3 is the temperature of the other side of the wall. Then this junction where these two slabs are meeting is having a temperature of T2.
Yes.
Okay, so we call this T2 temperature as interface temperature.
Okay, sir.
Interface temperature. So interface temperature is T2 here. Now, see, whatever is the heat transferred in the first slab, that will be equal to heat transferred in the second slab, and that will be equal to overall heat transfer. See, this term, what I have told you, is valid only under steady state condition. Are you able to understand this?
In the sense, if the temperature is linear, sir.
Temperature doesn't vary with respect to time.
Okay, sir.
So in that case only, what is the statement what I have told you? That means heat transferred in the first slab will be equal to heat transferred in the second slab. That will be equal to overall heat transfer in the composite slab.
Yes, sir.
So what is heat transferred in the first slab? From the previous learning, can we write T1 minus T2 by L by Ka?
Yes, sir.
So here L is L1, thermal conductivity is K1, area is A. Why area is A here? Try to observe carefully. We need to consider the area that is perpendicular to heat flow direction. Correct? For both the slabs, this is the area that we need to consider.
Yes, sir.
So this area will be same for both the cases.
Yes, sir.
So can we take A directly now?
Yes, sir.
For the second wall, can we take heat transfer Q is equal to T2 minus T3 by L2 by K2A?
Yes, sir.
Now, can I write this expression like this? T1 minus T2 is equal to Q into L1 by K1A?
Yes, sir.
From this, can I write T2 minus T3 is equal to Q into L2 by K2A?
Yes, sir.
These two we have got. Suppose if I add these two, what I will get? can I write this one like this? T1 minus T3. This is equal to Q into L1 by K1. Q can be taken common plus
Yes,
L2 by K2 A2. So this same diagram is represented in a two-dimensional way like this. Can you observe?
Yeah, sir.
So in a two-dimensional way, this is the way it is represented. Okay. Now try to observe carefully what I am doing. I want Q. Can I write this Q like this? T1 minus T3 by L1 by K1A plus L2 by K2A.
Yes, sir.
L by Ka, what we have written? RTH,
Yes, sir.
RTH conduction 1 plus RTH conduction 2. Okay.
Sir. Yes, sir.
Now, so we can represent this by using electrical analogy also. How do we represent that? Let us take some electrical resistance diagram in this fashion. Okay.
Yes, sir.
Right. So this is RTH conduction 1 resistance. This is RTH conduction 2. This side of the wall is at temperature T1, the other side is at temperature T3, and at the junction it is T2. Heat flow takes place in this particular direction. Got it now?
Yes, sir. Yes, sir.
So you can draw this bigger diagram or simply draw the resistances and solve the problem. Clear?
Yes, sir. Yes.
Okay. Now suppose for two slabs, this is the formula that we have got. Correct or not?
Yes, sir.
For two slabs, the formula is this particular thing.
Yes,
Suppose in the problem you don't know, he has given 3 or 4 slabs. Then what you will do? Then we will see a generalized formula for this. That will be Q is equal to T1 minus Tn plus 1. What is n here? The number of slabs.
Slabs. Yes, sir.
Okay. So when there are two slabs here, you can observe the outermost layer temperature is T3. Correct or not?
Yes, sir.
When there are n slabs, what will be the outermost layer temperature?
Plus 1.
Tn plus 1. Got it now?
Yes, sir.
Okay. Now, divided by, can we write like this? Sigma RTH n.
Yes, sir.
N is equal to 1 to n. Okay. So, here when there are two slabs, how many thermal resistances we are getting? 1 and 2. Correct or not? When there are n slabs, we will get sum of all these n things. Is it correct or not?
Yes, sir.
So this is how we need to solve. Clear?
Okay, sir.
Have you understood this?
Yeah, sir.
Okay. So this is composite wall. Okay. So in the last class we have discussed about this part, right?
Yes, sir.
So try to remember that derivation and these derivations. And if you can get the data book, these formulas will be available in the data book. We can solve some problems. Okay.
Yes, sir. Actually, tomorrow we have last lab practical, sir. So after the practical, go and get it, sir.
Yeah. Because if you know data book, problem solving is very easy. Okay.
Yes, sir.
So only thing what we need to learn is the short answer questions and this derivative part.
Okay, sir.